All right. So yeah, this is our last day of class. We don't have really new material to talk about today. We have a couple things I want to do as a review, both a specific review for stuff we did on Tuesday, and then also a little bit of more generic review in the context of this fun YouTube video that I watched a few months ago. So I want to talk about the exam to start out. The final exam. So it is cumulative. So it means everything we've done in the course will be on the exam. And generally speaking, at least, approximately the weighting of topics will be in proportion to how much time we spent in class. So let's see. It is Wednesday, May 4th. That's the last day of finals. So it's going to be a real circus getting all the grades back to us and into WebAssign and then into my pack, which is the official record, by Friday at 5 p.m. Let's see. The time is 7 to 9:30 p.m. It's in the same location that our midterm exams have been in Dabney 222. So note that the 7 p.m. is the actual exam start time. Previously, our midterms would start at 7:30 and end at 9. Now for the final, we're going to start at 7 and end at 9:30. So 2.5 hours of working on the exam. So that means please try to come a little bit before 7 if you can, so that we can get everybody in their assigned seats and get the tests passed out as close to 7 p.m. as we possibly can. And also, please interrupt me if you want. There's not that many people in this call, so you can pretty much just speak up. Or if you would rather, go ahead and type in the chat or raise your hand. Okay, so final exam will have 28 questions total. And so if you divide up that 2.5 hours, that's a little over 5 minutes per question. So a little bit longer per question than you would have on the midterms, which is good. But it gets better than that. What we're going to do is sort of similar to midterm 2. We're going to grade the best 26 of your answers out of 28. And so again, like the midterm, it means you can get 2 wrong and still get 100%. The minimum grade will be 7%. At least I guess that's what I calculated with 2 free questions. But what it does not mean is it does not mean extra credit. So you can't make above 100%. Okay. If you get all 28, you still just get 100. All the rules for the exam will be the same in terms of calculators, in terms of finding your assigned seat based on those 2 grade entries in your WebAssign account. It'll all be like that, just like it was. And I think everybody has done a really good job this semester in following the rules and being conscientious. So I don't anticipate any big problems. It's just a reminder. So as usual, my recommendation is that the homework is the closest thing you have to knowing the level and type of problem that will be on the exam. So really focus on going back through homework. Really focus on going back through the midterm exams that we've already taken this semester. I think those are absolutely your best study guide. And especially, I'm sure the vast majority of you are pressed for time. And if you have to make choices about what to do, looking at the exams and looking at the homework should be your priority. There will be a practice test on Moodle. I'm actually not sure if it's up yet. I can't remember, honestly. If anyone knows, you can speak up. But the practice test is intentionally sort of extra. So yeah, there's a question in the chat about, are the midterm tests and answers on Moodle? Yes, they are. I think it's only one version. Like I think it's typically we just put up version A. You should be able to find both of those. So yeah, the practice test is sort of really meant to be extra, and we make it on purpose, not like the exams, because a lot of us are aware of some of the problems that can arise when you give practice exams that are sort of too much like or too much to seem to be too much like the actual exam. People tend to over rely on it. And so we purposely make the so-called practice test very different. And so if you have time, going into the practice test can be a good way to identify weak points in your understanding. But I would say if you're struggling with time management, which is completely understandable at this time of year, focus on going back through the midterm exams and the homework. Okie dokie. Is this it? Is this all I have to say? I guess so. Let me go back one slide. Questions about any of these logistics before we move on? All right. You can always speak up again later if you think of something. Oh. All right. So here are my plans for how I'm going to do my own final exam reviews. So I'm going to keep our Monday afternoon Zoom chats from 2 to 4 p.m. So on this coming Monday, April 25th, and the following Monday, May 2nd, we'll just do our normal thing that we always do, where you pop in as needed and you sort of do whatever you want. And then as of now, I'm basically decided to do two other ones, just sort of Friday, the 29th, and Wednesday, the day of the exam, May 4th. I'm just going to be online from 11 to noon, available to answer questions. And that's a gap in between final exam sessions on those two exam days. So kind of like a good time to pop in if you have relatively short things to talk about. So if none of this works for you and you feel like you're likely to need some extended time, just contact me by email and we'll try to work something out. I think many of you should have gotten an email in the last half an hour from Dr. Webster. Dr. Webster will also be running a Zoom review on different days than what I've proposed here. And that's open to everyone in PY208. I'm not communicating my Zoom sessions to any of Dr. Webster's sections. Just, I guess, I don't have any reason to not do that. It's just that I don't have email lists of all those people, whereas she has email lists of everyone. So yeah, if you have friends in any of Dr. Webster's sections, they're also free to come to any of these if you want to send them the Zoom link. They should be able to access it on Moodle, I guess. All right. Questions, comments, concerns? All right. I'm going to move on and talk about, I want to do a quick example about refractive index type stuff. So we talked on Tuesday about propagation of electromagnetic plane waves. And so just a quick reminder, just make sure we spend enough total minutes doing it. Let's do an example together about Snell's law and talk a little bit about not just how to solve it, but maybe some ways to check our answer. So here it is. We're going to have a beam of light in vacuum that encounters a glass cover slip, right? And you're given that the glass cover slip has n equals 1.46. And the beam of light comes in at an angle of 40 degrees to the normal of the interface. And so what will the angle to the normal within the glass be? So what I want to do is give you about 3 minutes to work on this by yourself. This is just using ideas from our last lecture. And then I'll mute myself and set a little timer and we can talk about it. Maybe wait to the end. And what we'll do is in the end, we'll all put our answers in the chat, okay? After 3 minutes. All right, go ahead. Work on this for a minute. Oh no, go back. That's a picture, but I want you to draw that picture by yourself. Okay. So everybody just spam your answer in the chat. Like which letter do you choose? I'm gonna look at it. So I just want to say to everybody who's like a Call of Duty fan, I did not plan this way, but it is kind of funny. Getting a lot of F's in the chat. Yep. should have I should have planned it. All right, let's take a look at how you do this real quick. I see almost all F's, which I also agree with. Oops. Let's draw a picture. I, highly recommend drawing a picture. I think this problem is straightforward enough that you could probably get away without drawing it. But if I were taking a final exam, I would draw a picture anyway, just to make sure I was not getting confused. So we come in from vacuum where index equals 1. This is an important point, right? You're given in this problem that the beam of light starts out in vacuum, and you are expected to understand that in vacuum, the index of refraction equals 1, right? That in some sense is just the definition of index of refraction. We do not expect you to memorize any indices of refraction, except in vacuum, it better be 1, okay? So note that you're not given n equals 1 and 1 equals 1. You're just given the index of refraction of the material that's sort of less obvious. All right. And so you're given the angle of 40 degrees to the normal of the interface, which means this one, and that's good because that's the one we need to use in Snell's law. So let's just start to apply Snell's law. So it says n1 sine theta 1 equals n2 sine theta 2. And theta 2 should be the angle to the normal within the glass. That's what we mean by that. So I just plug numbers in. The only unknown is theta 2. So I'll solve for sine theta 2 is 0.44. And inverse sine gives me 26, which is definitely F. So, excuse me. All right. So straightforward calculation, just plug and chug, right? I don't think, and unless you miss class on Tuesday, nobody's struggling with this arithmetic. But let's just talk a little bit about do we have any tools to check our answer? Do we have any tools to understand if this makes any sense at all? Because, on these exams, there'll definitely be distractor type answers that sort of might be right, but are not. So what we've got here is a light ray that bends down toward the interface normal, the dashed blue line, right? And so when you go from a low index material to a high index material, that's that weird marching band into mud situation where you expect the perpendicular to the wave fronts to bend toward the normal. So this angle better be smaller than 40, okay? So that's an important check we can do on our work, that since we're going from low to high, theta 2 needs to be smaller. And so from that perspective, we could have ruled out a bunch of answers, right? We can't have 70 degrees, we can't have 59 degrees, and we can't have 90 degrees, because those are all bigger, and you would have to be going into a lower index material. That's not even possible if you're starting out in vacuum. You can also rule out 40, because 40 says there's no refraction at all, and the only way for that to be true is if the two indices of refraction were equal. So 40 can't possibly be right. 26 could definitely be right, and most of us got that answer. There's no reason from the beginning that 36 couldn't be right. Until you do the calculation, you're not sure. What about 0? Is there anything we can say about 0 degrees? maybe somebody on the call can give me some idea about, look at this calculation and think about what would have to happen to give a theta 2 of 0 degrees. Ah, yeah. So Michael says in the chat, n would have to be infinitely large. To me, that's the most interesting case. So just look at this work and you could see a couple of ways to make theta 2 equals 0. So the way that's kind of boring is if you just changed theta 1, and if theta 1 was 0, theta 2 would also be 0. That's boring. But the interesting way is go down to this line and note that keep theta 1 equal to 40, and you're dividing by the index of refraction. And so if you let the index of refraction get really large, let it go to infinity, then you would get sine theta equals 0, and therefore theta equals 0. So, I mean, that's an interesting possibility. Do we have an infinite index of refraction material? I mean, that's a complicated question. First thing we can say is 1.46 is not big enough, right? So you don't have to worry about the possibility of 0 degrees here. So we can rule out 0, and we only have to decide between 26 and 36. 26 is the right answer. I like the idea of, so how large an index of refraction can we get? And for most materials that light can actually transmit through substantially, indices of refraction are sort of like 1.2, 1.3, 1.5. You can get them in the 2 to 4 range too. So there's some interesting ceramic type materials that have sort of 2 to 4 indices. It's hard to get them really, really big. The way you can do it is you can take an ordinary material that has a relatively ordinary index of refraction, and then you can nanostructure it, right? You can sort of etch it down to nanometer scale dimensions, like nano pillars or nano other shapes. And the way you design those nanostructures can determine the effective index of refraction, what's sort of called like a metamaterial. And so that's a really interesting research topic. I don't know a ton about it. So if you have a lot of questions, you'll quickly exceed my knowledge. But it is a really interesting topic. And so it's like people who are thinking about making invisibility cloaks, or sometimes they call them invisibility shields, are thinking about manipulating effective indices of refraction by nanostructuring very often. Okay, yeah, so answer is F. These problems are straightforward. The only way this gets hard is if you have to do a little bit of trigonometry. And so a way I could make this problem a little bit harder would be, I could say, well, not give you theta 1, and instead say, oh, well, the light source started out, half a meter along the interface at a height of 1 meter above the interface. And then you have to do a little trig and convert it to the correct angle to be used in Snell's law. Okay. So that's sort of just, it's not that difficult, but you probably have something like that on your homework that's due tonight. From here, I'm basically going to move on and talk a little bit about this YouTube video that I find pretty interesting. Unless anybody has any questions or comments about some of this EM wave stuff. Some of it will appear in this video, of course, but all right. Yeah, so here's the thumbnail for this video that I watched a couple months ago. It's a very famous YouTube channel. It's called Veritaium, which is a specific person whose name I kind of forget right now, but I think most people just call that person Veritaium. And so the title of the video is The Big Misconception About Electricity. And then the thumbnail clickbait is energy doesn't flow in wires. And so you see that and you're sort of immediately incredulous, right? Certainly energy is flowing in wires. And I think that statement is strictly speaking not true, but there's a very important science point that's being made in this video, which I'll tell you about. Despite the fact that I have critiques of this video, and of course many other people on the internet have had critiques of this video since it was posted, it is quite good, and there are very good science points inside the video. So top comment on the channel I noticed this morning was from this person. I'm so glad this video exists. I used to completely not even understand how electricity worked, and now I still don't. And so I think that's fair. I think that's even that comment could probably be upvoted for this class, right? 11,000 upvotes. We can all add our thumbs up to that. I mean, honestly, I think that's the truth about science. Like if there's something important in science, it's probably complicated enough that a 14-minute video or a 16-week university course is not going to be quite enough to really hash it all out. Nature is actually difficult to understand. And jump in anytime if you want to make a comment or ask a question. You know, this is meant to be a little bit of review. It's meant to be a little bit enjoyable. So, you know, you don't have to just listen if you don't want to. So let me tell you the good things about this video, because I mean, I am going to critique it, but I also think it's worth saying there's a lot good here. The good point of the video is that the main reason for making the video is to emphasize how important electromagnetic fields are. They are so important, right? That's what this whole course is about, PY208. And electromagnetic fields transport energy, right? They must, right? You can send a radiative pulse out from an accelerating charge, and it can exert a force on another charge. So that somehow energy is being transported. And that's the really important point of this video that's really, really worth making. And there are also lots and lots of good points in the video made about details of power transmission and field distributions in circuits. That's all PY208 topics. It's also a really good introduction to what's called the pointing vector, which is something that we occasionally include in PY208, but we haven't for a couple of years now. I'm actually not sure why. I would have included it if I had been designing the course myself. But pointing vector is basically 1 over mu naught times E cross B, and it describes energy and momentum flow in electromagnetic fields. And so if you're an electrical engineer, I'm sure you'll hear about that at some point. So what's bad? The thing I don't like about this video is that I think there's too much in this video that tries to de-emphasize the significance of wires in circuits. And I think somehow the idea that the wires don't matter is an easy misconception to take away from this video, that is not worth some of the gains that you would get from watching this video if you're not watching it somewhat critically. There's definitely some assumptions in this video about how light bulbs actually work, which are not true. And that's a critique. And I mean, in my opinion, it's certainly not the case that energy does not flow in wires. You know, charge is moving. Energy is being dissipated as you heat up the hot filament inside the light bulb. So there's definitely energy transport inside of wires. I think it's just a question of like how much of it, how much is in the fields versus the wires is being addressed here. I mean, but really important point is it's the charges in the wire that are rearranging and moving that actually create the fields. And so even if you are happy with the argument that most of the energy flow is happening in the fields don't exist without the wires, right? They can certainly propagate away from the wires in empty space, but the wires are really controlling the fields, and that's why they're so important. And then there's one point in the video, there's a discussion of irreversible energy transfer to loads, and the load specifically is like a toaster. And that comment is basically sort of just, that's the only thing in the video that's really wrong and not just sort of overstated. So those are a list of my critiques of the video. And I'm going to talk about most of those. I'm not going to talk about the irreversible part because that's, more like thermodynamics. It's not really part of this course. Thermodynamics is one of my favorite topics. All right, so here's the setup. Veritaium wants us to imagine building a circuit that is really, really big. And the circuit's going to have a battery and a switch and a light bulb, right? And the point is that the wires are really, really long. And in particular, we want the wires to each be about 1 light second long, so that in going from one terminal on the back of the battery all the way around to the bulb, you go about 1 light second. So light second is a distance unit. Because the speed of light is a universal constant, we can use it to define a distance scale, namely, how far does light travel in half a second? That's always going to be an unambiguous answer because the speed of light is always the same in vacuum, right? And so the distance that light travels in half a second, okay, I made a typo here. I forgot to fix it. 3 times 10 to the 8th times 0.5 is 1.5 times 10 to the 8th, not 7th. Sorry about that. But yeah, that's the distance that corresponds to a half light second. So really, really long wires. And so the question that Veritaium wants us to ask about this unusual circuit is, when we close the switch, how long does it take for the light bulb to light up? Okay. And so the options are, it takes half a second, 1 second, 2 seconds, 1/c seconds, or none of the above. Right? And so, I mean, if you're doing this on an exam, like the none of the above is always a tempting choice, or not, depending on how you feel about your professors. But like among the actual numbers that are given, right, there are 2 categories of answer. A, B, and C are sort of representing pretty long times. And 1/c in units of seconds is going to be a pretty short time by many, many orders of magnitude in comparison with A, B, C. And so somehow conceptually, there's a big difference between A, B, and C and D, right? And so that's your main issue, is like, conceptually, do you think it's a long time or a short time? Right. And the question of, is it 1, 2, or 0.5 is more like, can you do the algebra correctly? Right. But in the first place, you might want to think about, okay, if 1/c is a possible answer, there has to be a reason why the time would be so short. Because if you're going at the speed of light, moving along the wire, it takes you half a second to get down this length and another half a second to get down this length. So that something going along here would take about a second, and that's a long time, right? So that's worth thinking about, that they're really different conceptually numerical answers. The Veritaium has 2 assumptions that they state very, very clearly here. The first assumption is that the wires have no resistance. I'm sort of fine with that. I'm not going to belabor it. The second assumption is really important, and it's going to come back again and again. And that is, Veritaium wants us to assume that the light bulb will turn on immediately. And what they mean by immediately is that when any current passes through it, however small it may be, right? And that's a really significant assumption, and it's sort of the crux of their entire argument about what the right answer should be among these choices. There's some unstated assumptions, like there's no capacitance associated with any of the objects. There's also no inductance. So in other words, no Faraday's law EMF effects. And another assumption, which is sort of related to the stated assumption, which is that the steady state is not necessary to light the light bulb up. So where am I going with this? What I realize in talking about this with the other section is that my real critique of this video is not so much in any specific thing that they say. My real problem with this video is in setting it up as a multiple choice where one answer is considered to be correct. The reality of this problem is there's a lot to discuss about this problem, and which answer you think of as the actual right one depends a lot on your assumptions. And there's a lot of discussion points about each individual part. And so I think this video would be almost unimpeachable if it did not have a multiple choice list of answers associated with it. Let me just remark, why does the light bulb light up? This is kind of a review topic for us. So a light bulb in the context of a Chebet and Sherwood analysis means let's just push current through a very thin wire. So we got a battery connected by thick wires with low resistance. And then there's a thin wire right here where the resistance is very high. And so in this high resistance, there are many, many more collisions between the mobile carriers and the lattice. There's energy transfer to the lattice. The energy transfer to the lattice causes the ions to vibrate with higher amplitude. So vibrating ions means accelerated charges, and accelerated charges radiate. So that's a sort of hand-waving picture of why are we getting light rays out of this thin filament. It's because these atoms are vibrating due to energy transfers. Okay. So again, an assumption in the Veritaium video is that no matter how small the current is in this little piece, it's always gonna be considered to be lit up, right? Which is not true in practice, right? It takes a certain amount of current to actually light up a real light bulb. So back to the question. When we close the switch, how long does it take the light bulb up, not the light bulk? So we have to admit that we need E fields, electric fields, to drive currents. And so what we need to know about this circuit is what electric fields are present and what magnetic fields are present. And can all these fields end up driving currents in the bulb, right? And so let's go back to our favorite picture of circuits from like chapter 18 or something like, I think it was chapter 18, right? We have this Chebet and Sherwood mechanical battery where we inject charges and surface charges rearrange to make a uniform field as we go along the wire that establishes the conventional current from positive to negative. Okay. And so this is sort of one perspective on how to get fields, right? Where you have a uniform field in the wire that's set up by the surface charge distribution. And this picture is actually in Veritaium's video. So this is a great thing. Like if you haven't watched this and you have some time, you might consider watching it, because almost every second of the video has a concept from PY208 discussed. And so you can see the uniform E field inside the wire. You can see the conventional current indicated as going in the direction of the field. And you can see the surface charge on the outside of the wire. And so a minor point that we could address based on our knowledge of surface charges is what's wrong with this cartoon that Veritasium has made? Can somebody tell me about it? Go ahead, Khaled.
Is it that the electric field should be coming from the surface charges and not from the charges actually moving in the wire?
That's a fair point. But I guess the thing I want to say is I don't think that's what's trying to be indicated here. I think they're trying to say that that's the net field due to the surface charges. So there's something else that's going on here that's missing piece in this cartoon that's present in our textbook. I'm going to go back a slide and see if anybody can notice it. Like, look at that. So this picture, this upside down circuit I pasted in, look at that circuit from your textbook and try to compare it with what Veritasium's cartoon showed on the previous slide. Can you detect a difference?
Is it that the surface charge is uniform in the Veritasium video?
That's right. Yeah, good point. Yep. A couple people are saying it. Yeah, so Veritasium indicates it in the cartoon as being uniform, so a constant number of coulombs per unit area or length. And we know from our analysis in chapter 18 that the surface charge is high near the battery terminal, and it gets a little bit smaller as you move away, and smaller, passes through zero, and then small negative to big negative. And so this is what's indicated in this gray area that I've shown, which is just a glow script simulation, right? The deep red is a high positive density, and the blue is a higher negative density, and then the pink is in between, right? And so you have to have a gradient to get the field to point in a specific direction. If the surface charge were absolutely constant, there would be no field in the interior of the wire. You have to have a gradient. So I'm not real mad about that. Like, I don't think that's a major issue in this video. I think it would have taken probably too long to explain why the surface charge needs to be non-uniform. So it needs to be high positive here, low positive here. But it is a minor point, and it's a review for our class, right? So you want to be comfortable with this idea that there's a surface gradient, and you want to be comfortable with how matter and interactions textbook represents it, just as schematically the number of plus signs decreasing as you go along the wire. Okay. All right, so let's take a look then, ignoring that, which is again a fairly minor point. This is a picture roughly of what the field distribution would look like outside of the wires due to the surface charge distribution. So again, it can't be perfectly right because we know the surface charge is high here and low here. And so there's no way you can get a perfectly symmetric electric field pattern with that type of asymmetric surface charge distribution outside of the wires. So it's a little bit off from that perspective. But it's okay. Like, to some extent, we're willing to sacrifice some accuracy for a good conceptual picture. And so Veritasium is here just trying to make the point that there are fields all throughout space. Let me make another remark. These are field lines, not field vectors. And so they're accurately indicating directions, but not magnitudes. And that is important because if you go very far away from these surface charges, the field is falling off, to some degree. And so way out here, the electric field due to the surface charge is small, whereas very close to the wire, it may be large. What else do we want to say? Somebody brought up in the other class something that I never thought of, which is we already brought up the fact that in Matter and Interactions textbook, we might choose to represent this light bulb as a really thin segment of wire. And if you made a really thin segment of wire between these 2 points, then the surface charge gradient in that thin segment of wire would be very, very different than the surface charge gradient in the thicker section of wire. And so, in fact, the field pattern that's actually true in this region is quite a bit different than what's indicated here. So that's something that's worth keeping in mind. And in particular, like every word that I just said depends in detail on how the charges have been rearranged within the wires. So the fields themselves are indeed outside of the wires. And indeed, they may end up being the ones that transport energy most efficiently. But all the details are really contingent on the specific distributions of charge in the wire. And then there's another thing that's really important, and this is probably the most important thing, I guess. And that is once we've set that up, the internal E field in the wires is driving a steady, constant conventional current. And that's making B fields that are these blue circles. Those are the field lines. So you're doing your current right-hand rule where your thumb goes in the current direction and your fingers curl in the B field direction. Right? And so there's definitely a B field here outside the wire. There's an E field outside the wire. And so it's conceivable that energy is being transported via those fields. They do indeed transport energy. But it's also really important that these field patterns are themselves set up by sources. And the sources are the charges are setting up the E field, and the steady conventional current is setting up the B field. Right? And so this picture is not a perfect view of this circuit, but a reasonably correct view of the circuit. But it's a circuit that's in steady state, right? If you have these perfect Biot-Savart circles and sort of nice established surface charge distributions, you have implicitly assumed that your whole circuit is sort of in steady state. So let's go back and ask what is the answer that Veritaium would like us to say? And the one that Veritaium wants us to say is D. They want us to say D for the following reason. They really want to focus on the role of the fields, and that's good because the fields are super important. What they want us to imagine is that when we close the switch, at that instant, what am I doing? I'm pressing the wrong button. Sorry. At the instant we close the switch, a charge in the wire gets an acceleration, right? And so let's say the acceleration is in that direction and it's like a positive charge. I don't know, whatever, it doesn't matter. All right. When that charge gets accelerated, at that very instant, it emits a pulse of radiation. So that's our radiative E field, where our observation direction is in the direction of the light bulb filament. So perpendicular to A. So that means the full A vector represents the A perpendicular. Right? And so the radiative field would be pointing away from A. Nope. And it propagates at the speed of light up toward the filament. So as soon as that radiative field, that little kink in the field line, gets to the filament location, it sees some current. And Veritaium has asked us to assume that any current at all will light the bulb up. And so as soon as we've got that radiative field, we automatically have a current, and therefore we assume the bulb lights up. And so the distance that the radiative pulse has to travel is 1 meter. So the radiative pulse has that magnitude. It's opposite to A perpendicular. And so then the idea is that if the pulse is going at the speed of light, it only has to go 1 meter, this little small distance. And so distance equals speed times time. We have 1 meter equals the speed of light times the time to travel. Solve for the time to travel. It's 1 meter over c. So that's 3 times 10 to the minus 9 seconds, or 3 nanoseconds. Okay. So this is the answer that Veritasium wants. And there's a lot of value to this answer because this physical picture is true. There will be an accelerated charge. There will be a radiative pulse. Whether the light bulb will light is a quite separate question, right? That radiative field is likely to be quite small. You've got a 1/r dependence, right? So it's falling off with distance as you go away. So it's not clear that there'll be enough current in the light bulb to actually light it up due to this radiation effect, right? So the way that Veritasium can be sure to be right is by insisting that we make this assumption that the bulb turns on immediately when there's any current at all. And so it's slightly misleading, in my opinion. And it's slightly misleading because the setup sort of draws a picture that's rather implying a steady state in the whole circuit has been reached. And the truth is, the answer that Veritasium wants is the transient, where there's only been time for radiation pulse to travel across the gap and cross the filament position. And so it sort of looks like this scenario where in 3 nanoseconds, only a small part of the circuit is in anything resembling a steady state, right? If you're farther than a meter away from the switch at 3 nanoseconds, you don't even know the switch has been closed, right? And so it's nothing like a steady state configuration unless you're in this really small 1 meter square region near where the switch closed, right? And so that region would look sort of like the conventional steady state circuit field distribution, but everywhere else doesn't even know the switch has been closed and nothing interesting is going on. In particular, there's no fields, right? There's no fields there at all. So we need to wait a long time to get anything close to the steady state distribution, right? So to get all the surface charges to rearrange around this bend and establish a steady state current that gives us our Biot-Savart ring fields, you got to wait about a second for it to travel all the way to the wire. And so if you imagine what it means to light the bulb as when does the bulb behave as though it's in steady state, it's much closer to a second. It's probably a little bit more than a second for influences to travel from the switch around the whole wire to establish this configuration. And so it's not saying that the fields aren't important, right? But it is saying that fields are produced by matter, right? And so in order to get the circuit to behave the way you want, you need to use matter to create the sort of steady state controllable condition that you normally expect. So here's my summary for what I think about this. Actually, let me go back before the summary and say one thing. 3 nanoseconds. Does nanoseconds remind you of any time scales that we talked about in this class so far? Like we typically, like we sometimes talk about time scales, like how long does it take? I mean, you could have a nanosecond RC time constant, but yeah, I don't, that depends on the values of R and C. Like what's just a generic hokey thing we say sometimes that's sort of nanoseconds? It's related to this picture of the fields. So remember, like we talk about how drift speed is kind of getting close. Like in a typical circuit, we say, how long does it take for the surface charges to rearrange to establish the steady state condition? And we typically say, if you read your textbook and probably my lectures as well, it's something like a nanosecond, right? But the reason we say that is because most circuits are about a meter, give or take, in dimensions, right? And so when you think about how to propagate at the speed of light around the whole circuit, it takes about a nanosecond or a few or half or whatever, right? Order of magnitude nanosecond, right? But if you make a ridiculously huge circuit that's 1.5 times 10 to the 8th meters wide, right? That's no longer valid anymore. It now takes seconds for the charges to rearrange. It takes seconds for the currents to be established, right? And so that was an assumption that was implicit back in our discussion, was that we felt like, well, if we're dealing with normal size circuits, everything happens in about a nanosecond. But then when you make this ridiculously huge circuit, that's no longer true. So that was a place we heard about nanoseconds from our past work, like how quickly do surface charges rearrange? Right. They rearrange that quickly on the condition that the circuit itself is in every dimension of order about a meter. But if some dimensions are super long, you need to take into consideration things can only propagate at the speed of light. Okay. So yeah, let me do a quick summary. I do want to say, I feel like I'm sort of critiquing this, but mainly it's just for fun. I think Veritasium's video is extremely good and has a lot of valuable insight. I mean, I'm just like, almost everything in the video is great. Almost every idea is sort of valid and making a good point that you should know about. There's only one thing that's kind of wrong about the irreversible energy transfer, but the bad part is this idea that 1/c is the right answer because it's so contingent on some of the assumptions. And I think if you took out the multiple choice part from the video, it would be, like I said, and like an unimpeachable video that's just really cool science ideas and really, pointing out how important it is that electric and magnetic fields can transfer energy from place to place, right? But it does take substantially longer to achieve a steady state. And that's because of point number 4, right? Charges are the sources of the fields. Static charges make E fields, steadily moving charges make B fields. And so even though energy is transported substantially by the fields themselves, the role of the wires in controlling the fields is so important that you really don't want to de-emphasize it, right? Because it's really how you think about like designing circuits, and sort of the reason fields exist is the properties of that matter. Yeah, so that's my discussion of Veritasium's video. There's a bunch of like electrical engineering type people who have made sort of response videos as well. I didn't actually cite any of them. I only watched one, but I've seen like a long list of, OMG Veritasium wrong. So I think that's it for today. I'm going to hang around until 4:15 if anybody wants to talk about any course logistics or homework or whatever. Otherwise, I'll be sending out reminders for the various review sessions, and I'll see you on May 4th. I appreciate everybody working hard and, being good students this semester, especially making the exams go smoothly. So we'll talk again later on.
All right. Thank you.
See you later.